Hello everyone. Today I'll be talking about how we can store two-dimensional data in R and how to manipulate those R objects. So as we talked about last time, one-dimensional data is stored in a vector, and that vector is created using a function. I typically use the C function to create vectors, but there are other functions that will output a vector as well. For matrices, we're also going to use a function. So with matrices, if I want to create a matrix called myMatrix, I'm going to use the matrix function. And you'll notice I have the help file pulled up over here. As a reminder, you can pull up help files by doing !matrix, and that will open the help file in this window. So matrix is going to take a few different arguments, which means it needs to be given certain sets of information to do what you want it to do. So the first argument is data, and that's just whatever values you want in your matrix. So I'll just say I want the values 1 through 20. We'll make a numeric matrix. And n row is how many rows you want in the column, and we also can specify n col. So let's just be explicit with what each of our arguments are. You don't actually need to be explicit by having like data equals here. Matrix will automatically know that the first argument you give it is data, the second argument is n row, and the third argument is n col, but you can be explicit, and I think for clarity we'll be explicit today. So we'll say we want 4 rows and 5 columns, and we'll say by row equals to false. So what this is telling the matrix function, this by row argument, is it's saying I want you to fill in the row, or fill in the matrix, not by row, but by column, by having by row set to false. So I'll show you what that means. So let's make my matrix. If I click on this, we can view it. And we see that it is a matrix with 4 rows and 5 columns, just like we wanted. And it's been filled in by column. So the first column is 1, 2, 3, 4, second column 5 through 8, etc., all the way down to 20. If I instead set this by row value equal to true, now my matrix is filled in by row, so 1 through 5 at the top, going down all the way to 20. So we'll just leave it like this for now. So we've now created a matrix, but what can we do with it? So what can you with a matrix? You can do simple math with it if it's a numeric matrix. So if I do +1, you'll see that just like with vectors, taking my object and added 1 to each value in the object. So we have a matrix that was 1 through 20, now it's 2 through 21. You can add another matrix, and we'll just make a new line here for that. And that works fine. As you might imagine, as with vectors, it is most useful to do this when your matrices are the same size. Let's see what happens if you have matrices of different sizes. So my small matrix, and for this one, we'll just have the values 1 through 10, and row equals 2, and col equals 5 again, and by row equals true. So now we have a smaller matrix that has half as many rows as our first matrix, okay? So let's try to add those together. And you'll see that unlike with vectors, where you can take vectors and add together vectors of different lengths, you can't really do that with matrices. So they say it's non-conformable arrays. It's an error. It didn't produce any output. Basically, R said, I don't know what to do with this. So this throws an error. So just note that that's something slightly different than with vectors, whereas with vectors it would recycle the smaller vector. It does not recycle smaller matrices here to do addition like this. Okay, so simple math is one thing you can do. What if you want to extract certain rows or columns from a vector, or from a matrix, excuse me. So let's look back at my matrix, and let's say I want just this first row. I don't want rows 2 through 4 for whatever reason. So if you remember with a vector, you do indexing with square brackets, and then you just enter a number or a vector of numbers or a vector of logic values, etc., to pull out values. It's very similar when we're talking about indexing matrices. So if I do my matrix, you do the square brackets just like you did with the vector, but now you need two values. So the first value is going to be rows. So um, this isn't real code, but just to show you that if you want to index a matrix, you put your indexes for rows, then a comma, and then your index for columns. So if I want just the first row, I will do this, and I'm going to leave the second area after the comma blank because I want all of the columns. So if you want all of the columns, you can either put in a vector with the numbers for all of the columns, or you can just leave it blank, and R knows that you want everything. So this gave us 1, 2, 3, 4, 5, which is our first row of our matrix. Okay, what if I want just the first, well, let's say I want the third row, fourth column. You do a 3 and a 4, you get the number 14, and you'll see that indeed that is the value in the third row, fourth column of our matrix. Okay, pretty simple so far. What if I want, let's think. Let's say I want um, all values that are less than 10. Let's say I want all values that are less than 10 for my matrix. So if you remember from vectors, the way we did this is a few different ways. So first, we just input the numeric positions of all of the values less than 10 manually, and then we input a logic vector where we had a true in each position that had a value less than 10, and we made that manually. And then we learned that you could do you could make a logic vector by doing a comparison. So if I do my matrix less than 10, that's going to work very similarly to what happens when you do it with a vector less than 10. It creates a logic matrix this time instead of a logic vector, where it has true at every position we want to extract from the matrix and false at every position we don't want. So how does this work with a matrix? So my matrix. Now notice what I've just typed should look a little bit odd to you because up here I just told you that you need two values to index a matrix. You need a value for rows and a value for columns. But as it turns out, you can also use a single value to index it, assuming that that value is a matrix. And there are actually ways to do it where that value is a vector as well. So I could do this as dot vector. And if I do this, this my matrix less than 10 wrapped in as that vector will now return a vector instead of a matrix. And if I put that in here, you'll notice that it still did the index just fine. And that's one thing to note is that matrices in R are actually just a special case of vectors. So there are ways to index things with vectors, but by far the most helpful way to think about indexing vectors is to think about either selecting rows and columns. And again, this doesn't have to be a single value. So you could do, if I want both columns 1 and 2 in row 1, I could do a 1 for row 1 and then make a vector of the values 1 and 2 for the column, and you'll get columns 1 and 2 in row 1. But by far the most helpful way to think about indexing vectors is inputting values for the rows and the columns, or inputting values as a matrix to pull out those values. Okay, so we've now extracted values less than 10. Great. You'll notice that when we did this, it extracted as a vector, not a matrix. So we went from a matrix to a vector, and the reason that happened is because when you're just extracting random values from a matrix, it's not going to conserve the rows and columns that you had in the original matrix. So you can't you can't present that data as a matrix anymore. It now needs to be converted to a one-dimensional data set, which is a vector. Hope that makes sense. Okay. One other thing we should talk about with matrices is that they have rows and columns, and the names here are pretty uninteresting. Let's say we had made a matrix. And again, often you won't really be making matrices like this by hand. You'll be importing them from a spreadsheet. But say you do want to make a matrix and you want to name your rows and columns something other than 1, 2, 3, 4, and B1, B2, etc. So the way we do that is with the call names and the row names function. And these behave a little bit differently than other functions in the syntax, so we'll spend a little bit of time making sure it's clear. So naming rows and columns in matrices. Okay, so normally you think of storing an object as you name your object and then you have a value to input into that, and then you do something over here that will get stored in there. With naming rows and columns, what you're actually doing, let's say we want to name the columns. So if you just do call names my matrix, what this does is it pulls out the object that is the column names for my matrix. And there aren't any at the moment, it's null. So if I want to assign some, which I can certainly do, I can create a character vector here, and we'll say column 1, column 2, column 3, column 4, and then we'll just say random text. So since this is actually an object, it's not just pulling up names and outputting them. It works a little bit weird. This is actually an object. We can store something in it, and what we're storing is text that will become the column names of my matrix. So now if we go to my matrix, we'll see that we have changed the column names to the text that we had input. So just note, if you're changing column names, this is the syntax that you want to use. You use call names, wrap whatever object has columns that you want to be renaming, and then go ahead and assign things. Let's say I want to change only some column names though. So let's say we want to change the name of the second column. I can do this by doing my matrix and then indexing this, and we want to change the second value, and we'll say new name. And now if we go to my matrix, we'll see that we have changed just the second column name. Row names work exactly the same. Row names, my matrix, A, B, C, D, and we'll see that we have renamed the rows. Okay, so that is matrices. We'll just indent this. One thing to note is that all of the data in our matrix right now is numeric, and there's no way around that. Matrices, by definition, always contain all values of the same type. You can have a character matrix if you want. So if we just do a character matrix and we'll store it. So our data will just say A, B, C, D, and n row equals 2, n call equals 2. I don't really care if it's by row or by column. So we've now made a character matrix. We obviously can't do math like this. So this is the same as with vectors. If you have a character object, you're not going to be doing any math with it. If you have a character vector of numbers, you can convert it to numeric using certain functions. But I don't want to get into that for matrices right now. Just be aware that matrices have a type. They can be numeric, they can be character, they can be logic. Okay. Let's talk about what happens, though, if you want two-dimensional data with mixed data types. So let's say you have a table where some columns are going to be text, say the names of individuals, and other columns are going to be numeric. A matrix won't work for that, so what you need instead is a data frame. So my df is what we'll call ours, and we make data frames using the data.frame function, and we can get the help file for that down here, and we'll see that data.frame creates data frames, and the input is just dot, dot, dot. So that's not particularly helpful to see that. So I have to come down here and read the arguments and see that these are either the form value or tag equals value. So what that means is I can input a vector here. So one thing to note with data frames is that each column is a vector. So in that sense, each column by itself has to be consistent on its data type. So you can't have a column that has both text and numbers in it and expect R to know what to do if you try to do math with that column. So first column is going to be all numbers, all character, all logic. Now, of course, text could have numbers in it, but just being stored as text. But the data type that R sees is going to be the same for a given column. But different columns within a data frame can have different data types. So let's say our first column is going to have some numbers, so we'll do the numbers 1, 2, 3. And the second column is going to have some text. So we can do a data frame like this. This is essentially using the value form of the input into the data frame, and you see we now have a data frame where we have our numbers, we have our letters. If we click this little arrow here, we can see that our first column is indeed numeric and our second column is character. But our column names are pretty hard to use, definitely not what we want. So that's where this tag equals portion comes in. We can name our columns while we're inputting the data into a data frame. So we can say my nums equal and my cars equal. And now when we make our data frame, that will have named the columns whatever we wanted them to be named. Just a note, if you want to rename the rows in a data frame, it's exactly the same as with the matrix. You use the row names notation just like we did with the matrix. Okay, so we now have a data frame. It's not that interesting. Let's make a more interesting data frame that we can maybe do some practice with. So let's, by the way, I haven't mentioned this before, but I probably should. Anytime you see a function name complete instantaneously, that's not me typing really fast. What's happening is as I type out the names of functions or variables in R, RStudio is suggesting autocompletes for me. And once I get to the point where it knows which one I want and it's highlighted, I can just press Tab, and that will autocomplete the name of the function for me, or the name of the variable if I'm calling a variable. Just a quick tip to help you type faster. So we're going to make a data frame here, and let's do some names. So we'll do Alex, that's me, and then we'll do Bob and Linda and Jill. Okay. Next, let's do favorite numbers. So favnum. And let's just make up some numbers here. And then let's do fav color. And we'll just do red, green, blue, yellow. Okay. So now I have a data frame called BetterDF with 4 observations of 3 variables. So we have a names column, which is character, a favorite number column, which is numeric, and a favorite color column. So let's do some practice indexing with this. So indexing data frames, and the first practice is going to be extracting just the names column. Okay, so there are a couple of different ways to do this. So the first way is probably what's coming to mind to you if you paid attention during the matrix portion of this video, is we do square brackets. It's a 2-dimensional object. Surely we can just take all the rows and take the first column, and that does work. Now we have extracted the names. With data frames, though, there is a different way to extract a single column, and that is using the $sign. Because each column is its own vector, this essentially allows you to pick whichever vector is being stored in the data frame very quickly. So if I want BetterDF names, I just type betterdf $names, and now that will also extract that vector, which is the first column. Okay, that's fine. Let's say I want extract second and fourth. We'll just switch it up and do colors. Okay, so for this, we want to extract the favorite color vector, and then this is just a vector. So if we want the second and fourth values, we just put in a vector of 2 and 4. And there we go, green and yellow. Okay, so that's good. That hopefully looks somewhat consistent with what you've been seeing for vectors and matrices so far and is making some sense in your head. If it's not, I encourage you to just pause the video and take a minute to play with data frames, make a data frame, and just try doing a few things until it makes sense. Okay, let's do something a little bit more complex now. Let's take and extract all names with a favorite number less than or equal to 3. Okay, so for this, take a second, think about how this might be accomplished based on what you've learned so far, and hopefully what's coming to mind is that we can extract the names column, and we want to subset that. So we want a subset of the names column, so we're going to take betterdf $names, but we want to subset it using a vector based on whose favorite number is less than or equal to 3. So for that, we can do betterdf fav number less than or equal to 3. And this will give us the names of Alex, Linda, and Jill, who are the people in our table who have the favorite number less than or equal to 3. Okay, so why did this work? Remember that when we take a vector and do a logical comparison, that creates a logic vector. In this case, this created the logic vector true, false, true, true. And when we input a logic vector into the index of a vector, in this case the betterdf names vector, that will extract the first, third, and fourth values. So that's why that works. I hope that makes sense to you, because it's only going to get a little bit more complicated. So let's say now we want to extract all names with favorite color green or blue. Okay, so this is going to introduce something new. So far, all of the logic comparisons I've been showing you to make these logic vectors have involved numeric considerations, doing less than, equal to, etc. I should probably, that reminds me, I should probably mention that if we want, let's say we just want all names with a favorite number equal to 3, I should probably mention that the notation for that is 2 equal signs in a row to create that logic vector. So this creates a logic vector, and then this would pull that out. So just note, if you're doing an equal to comparison, you need 2 equal signs, not just 1, because if you use 1 equal sign, R thinks you're trying to create a new vector or a new object of some sort. Okay, so I digress. Back to extracting all names with a favorite color, green or blue. So let's talk about doing comparisons with text to create logic vectors. So we'll do this using the favorite color vector, of course. And you'll notice this has 4 values, red, green, blue, or yellow. And what we want to do is find the positions that are either green or blue. Now, there are a couple of different ways to do this. The cleanest way, in my opinion, is to do % in % and then a vector of the values that you want to look for. So if I do green or blue, you'll see that what it did is it looked through the vector, and for each value in that vector, it asked, is it in this vector, which is green or blue? So red is not in that second vector. Green is, so that produced a true. Blue is, that produced a true. Yellow is not, it produced a false. So now we have our logic vector, which is what we need to do this indexing. So we can just input this here. And there we go. We got Bob and Linda, who's indeed are the two people with favorite colors, green and blue. Okay. I said there are a couple of different ways to do this, though. So what's another way? Another way is if you don't feel like working with a logic vector for whatever reason, you can also turn this into numeric positions. And this is just a trick with the which function. So which, W-H-I-C-H, is going to produce a numeric vector every time there's a true. They're going to pull out the numbers of each position where a true is found. So remember, this is false, true, true, false. If I throw this into the which function, we now have 2 and 3. So it has looked at this logic vector and found the positions where where the values are true. And remember, if you have these numeric positions, you can put them into a vector and extract the values. So we could put this in there as well. Doesn't seem particularly useful, obviously, because it's just more code to do the same thing. But just a helpful illustration of the which function existing, because you do need that sometimes. There are other ways to create logic vectors with text, but I think this is probably enough for you to get started, and Google can be your friend later if you need to learn about grep and regular expressions and things like that, which maybe we'll cover in a later video. Okay, so far we've learned that if we want to store two-dimensional data, we can store it in a matrix with the condition that in a matrix all of the data in all rows and columns has to be the same type, either all numeric, all text, or all logical. We can also use a data frame, which allows us to have each column have its own data type. So you can have a numeric column first and a character column second, etc. All right, what if we want to start modifying our data frames, though? So let's talk about adding a column to a data frame. So let's say we have our BetterDF data frame, and what we want to do is add another column which is just trues and falses for whether or not someone's favorite number is less than 3. So the way we would do this is we can take BetterDF, $, and then the name of our new column, and we're going to store a value in there. So essentially what we're doing is we're asking R to look for the new column in BetterDF. R is going to look and see that that column doesn't exist, so it's going to make it for us, and it's going to store in that column whatever we put over here. So we want, I guess I'll make this explicit, add column true, false for whether is less than 3. Okay, so hopefully you kind of have an idea how to create that logic vector, BetterDF, favnum, less than 3. Run that code and we'll see that now we have added a new column to our data frame where it is true every time favorite number is less than 3. Okay, what if we want to add more data to our column? More data to our data frames. Not necessarily more columns, but more rows. Well, for that, we are going to do a row bind. So let's add extra rows to BetterDF. Now, normally you're going to have two totally different data frames with different data in them that you're wanting to combine, with the condition, of course, that if you're adding new rows, both of those data frames need to have the same column structure, because if you just add them together and they have completely different columns, it doesn't really make sense to combine them by row. But in this case, I don't feel like making two different data frames, so I'm just going to make a larger df that is BetterDF added to BetterDF. And the function we'll use for this again is rbind, which stands for row bind. So here we're just going to do BetterDF with BetterDF, and that gives us larger df, which now has duplicated those two data frames because that's what I told it to combine, is that data frame with itself, and it added it by row. There's also a cbind function if you want to add columns to a data frame from another data frame. Keep in mind that with cbind, you'll need to have the same number of rows for that to work. And also keep in mind that rbind and rowbind work for matrices as well, of course, keeping the same number of columns or rows respectively. Okay, so that's great. Let's talk a little bit more about indexing because there's something I forgot to mention, and that's what if I want to extract just a couple of columns. So you'll often find cases where you have data frames with lots of columns and you only need a subset of them for a downstream analysis. So maybe you want to simplify your life by subsetting to just the columns you're interested in. Let's say get only names and favnum column. So we can do this in a couple of ways that you'll know and maybe one that you haven't quite thought of yet. So if we do better df, so we want two columns, we want all the rows. So again, it's rows and then columns. Think about, to help you remember that, think about the fact that rows are on the left, and if you read left to right, you're going to hit your rows before you hit your columns. So left to right, rows, then columns. So we want all rows, and we want the first two columns, right? Because we want the names and favnum columns. So I can do our normal sort of indexing where I put in a 1 and a 2. Okay, that's fine. But what if you have a large data frame with maybe hundreds of columns and you want dozens of columns and you don't feel like finding the index manually for all of those? Well, you can also use call names very effectively here. So if I do better df, I want all rows again, but now I can say I want all of the columns where the call names of better df are in the vector of columns that I would like to keep. So I want, just remind myself exactly, so it's lowercase names and then favnum. So what this is doing, call names, better df is again creating a vector of the name, the column names of my data frame. Remember, in is taking each value in the left vector and looking at whether or not it exists in the vector on the right. And my vector on the right is names and favnum, the two columns that I want to find. So if I run all of this together, you will see that it found that the first column is in the second vector. The second column is as well. Third and fourth columns are not. So now I have true, true, false, false, which is the logic vector I want to pull out just those column names that I am interested in. And you can do this with row names as well on the other side of the index if you want. So I forgot to mention that. It's something you'll use pretty often, so hopefully that's helpful for you. All right, so let's recap. I think that's about where we'll stop today, is that matrices store two-dimensional data all of the same data type. They are indexed with two values, although they can be indexed with a single value as well, which works with matrices, but not to my knowledge with data frames. I should point that out. Two-dimensional data can also be stored in a data frame where each column is its own separate vector with its own separate data type. And it can be indexed differently than matrices using this $sign if you just want to pull out a column, which you'll do quite a bit, especially as you create comparisons where you try to sort based on a single column, etc. Okay. There are, of course, other things that we could show you here, such as how to merge different data sets, but I think we'll leave that for a different video and just settle now. Hopefully you've been able to understand this and you now have a good sense for how you can store one-dimensional and two-dimensional data in R.